Tonight, we are going to talk about distance. Real distance. The kind of distance that makes everything we have ever built look completely useless. We are going to ask one question. How long would it take us to travel 1 light year? And when you understand the answer, really understand it, not just as a number but as a reality, you will never look at the night sky the same way again. 1 light year. It sounds simple. It sounds like something manageable. It sounds like a number you could look up and understand in 30 seconds. But the more you think about it, the more you sit with it, the more it opens up into something that breaks the way the human mind normally works. It is not just a big number. It is a number so large that it stops meaning anything at all the moment you truly confront it. And that is what we are going to do tonight. We are going to confront it. We are not going to look away. We are not going to let the number wash over us and move on. We are going to sit with it. We are going to turn it over and look at it from every angle. And by the end, I promise you, you will feel it in a way you have never felt it before. Before we get into it, if this kind of content makes you stop and think, take a second to subscribe. It helps this channel grow and keeps more videos like this one coming. Now, let us start from the very beginning. A light year is not a unit of time. This is the first thing most people get wrong. When they hear the word year, they assume it is measuring time. It is not. A light year is a unit of distance. It is the distance that light travels in 1 complete year. And to understand what that means, you first have to understand how fast light actually moves. Light travels at 186,000 miles per second, every second, without slowing, without stopping, without any effort at all. 186,000 miles, every single second. 186,000 miles per second. Let that be a real number for a moment. Not a fact you absorb and move past. A real number that you try to picture. 186,000 miles in 1 second. To put that in context, the circumference of Earth, the distance all the way around our entire planet at the equator, is about 24,900 miles. In 1 second, light travels that full distance more than 7 times. In 1 second, not 1 minute. 1 second. While you blink your eyes, light has gone around the world 7 times. While you draw a single breath, light has circled the planet more than 20 times. 7 times around the world in 1 second. That is what light does every single second of every single day. Right now, as you sit and watch this, light is circling the planet again and again and again. 7 times per second, never stopping, never slowing. That is what light does. Think about what that means for distances we care about. The moon is about 240,000 miles away from Earth. Light reaches the moon in just over 1 second. Just over 1 second. We could not even count to 1 before the light has already arrived. The sun is about 93 million miles away. Light takes about 8 minutes to travel from the sun to Earth. 8 minutes. For 93 million miles. The planet Jupiter, when it is at its closest to Earth, is about 365 million miles away. Light covers that distance in about 33 minutes. These are distances within our solar system, our neighborhood, the small, quiet corner of space where we live. And light covers these distances in minutes, in seconds, in moments so brief they barely register. And yet, even at that extraordinary speed, 1 full year of constant travel adds up to something almost incomprehensible. A year has 365 days. Each day has 24 hours. Each hour has 60 minutes. Each minute has 60 seconds. Multiply all of that together and you get 31,536,000 seconds in a single year. 31,536,000 seconds. Light moving at 186,000 miles per second for every one of those seconds covers a total distance of approximately 5.88 trillion miles. That is 1 light year. 5.88 trillion miles. 5,880 billion. Written out, it has 12 digits. 5,880 billion. Miles. That is 1 light year. That is the distance we are asking about tonight. That is the distance we are going to try to cross. And the question is simple. How long would it take us? Not light, us. With our rockets and our spacecraft and every tool our civilization has ever built. Let us begin with the fastest object humanity has ever created. Not the fastest thing we have imagined, not the fastest ship from a film or a novel. The actual fastest human-made object that has ever existed, the Parker Solar Probe. The Parker Solar Probe was launched by NASA in August of 2018. Its mission was to study the Sun from closer than any spacecraft had ever approached. Not just near the Sun, inside the Sun's outer atmosphere. Into a region called the corona where temperatures reach millions of degrees and the solar wind begins. To complete this mission, the probe had to orbit the Sun in tight ellipses, coming closer with each pass. Each time it approaches the Sun, gravity accelerates it faster. At its closest approach, the Parker Solar Probe reaches its maximum speed, approximately 430,000 miles per hour. 430,000 miles per hour. The fastest any human-made object has ever moved. The all-time speed record of our entire civilization. 430,000 miles per hour. Let us try to feel that number. A commercial airplane travels at about 575 miles per hour. The Parker Solar Probe moves 750 times faster than that airplane. A rifle bullet travels at about 2,000 miles per hour. The probe moves 215 times faster than that bullet. The fastest jet aircraft ever built, the SR-71 Blackbird, flew at about 2,200 miles per hour. The probe moves nearly 200 times faster. If a rifle bullet and the Parker Solar Probe started at the same point and raced, by the time the bullet had traveled 1 mile, the probe would be 215 miles ahead. That is how fast we are talking about. 215 bullet lengths ahead for every bullet length traveled. By every measure of speed that exists in daily human experience, 430,000 miles per hour is extraordinary. It is almost incomprehensibly fast, and it is still more than 1,500 times slower than light. More than 1,500 times slower than light. Our absolute fastest. Our greatest achievement in velocity. The record holder. The benchmark of our civilization's ability to move through space. And it is 1,500 times too slow to match the speed of light. Not twice too slow, not 10 times, 1,500 times. The gap between the Parker Solar Probe and the speed of light is not a gap that will be closed by the next generation of rockets. It is not a gap that engineering improvements over the next century will bridge. It reveals something fundamental about the scale of what we are up against. It reveals that light years are not just large distances. They are distances of a completely different order than anything our technology can currently address. So how long would it take the Parker Solar Probe to travel 1 light year? 1 light year is 5.88 trillion miles. At 430,000 miles per hour, that works out to approximately 1,560 years. 1,560 years. 1,560 years. Not decades, not a few centuries. 1,560 years. The Western Roman Empire collapsed in 476 AD. Count forward 1,560 years from that moment and you arrive at roughly the year 2036. We are living just about at that mark right now, which means that if the Parker Solar Probe had been launched the day the last Roman emperor was deposed, it would be arriving at the 1 light-year mark roughly today. The entire span from the fall of Rome to the present. All of the Dark Ages, all of the Middle Ages, the Crusades, the Black Death, the Renaissance, the Reformation, the Age of Exploration, the Scientific Revolution, the Industrial Revolution, the invention of electricity, the invention of the telephone, the invention of the airplane, World War I, World War II, the space age, the digital revolution, the internet, all of it. And the probe would only now be crossing the 1 light-year mark. And that is just 1 light-year. The nearest star to our Sun is Proxima Centauri, at about 4.24 light-years away. At Parker Solar Probe speed, reaching Proxima Centauri would take more than 6,600 years. The first permanent cities appeared on Earth roughly 6,000 years ago. The first writing systems were developed about 5,000 years ago. The pyramids at Giza were built about 4,500 years ago. Humanity has not had writing as long as it would take our fastest spacecraft to reach the nearest star. The nearest star. The single closest star to our Sun. Not the center of the galaxy. Not some far corner of the Milky Way. The nearest neighbor. And it would take our fastest probe longer to reach it than humanity has had written language. Longer than human civilization has existed in any organized form. Now let us look at the other direction. Voyager 1. Voyager 1 was launched in 1977. It is currently the most distant human-made object that has ever existed. More than 14 billion miles from Earth. Beyond the orbit of Neptune, beyond Pluto, beyond the outer boundary of the heliosphere, the bubble of solar wind that our Sun blows out into surrounding space. Voyager 1 has crossed into interstellar space, the empty region between star systems, and it has been traveling continuously for nearly 50 years without stopping. Voyager 1 was built for distance. It was built to go as far as possible, to study the outer planets and then keep going. It is our most experienced deep space traveler, and after nearly 50 years, it is still operating, still sending signals home. Faint signals that take more than 20 hours to travel from Voyager to our receiving stations on Earth, even traveling at the speed of light. 20 hours at the speed of light, just to receive a transmission from our own probe. Our own spacecraft that we launched. 20 hours for the signal to arrive. Voyager 1 moves at about 38,000 miles per hour, slower than the Parker Solar Probe, but still by any standard we normally use, remarkable. At 38,000 miles per hour, you could travel from New York to Los Angeles in about 4 minutes. You could circle the entire planet in about 40 minutes. You could reach the moon in about 6 hours. By every everyday measure of speed, 38,000 miles per hour is extraordinary. So how long would it take Voyager 1 to travel 1 light-year? At 38,000 miles per hour, the journey would take approximately 17,600 years. 17,600 years. 17,600 years. Not 1,560 like the Parker Solar Probe. 17,600. Agriculture was invented about 10,000 years ago. Writing was developed about 5,000 years ago. The entirety of human civilization, from the first cities to the present day, spans about 6,000 to 7,000 years. Voyager 1 would need to travel for more than twice the entire history of human civilization just to cross a single light year. More than twice. The whole of everything we call history and civilization would not be half the journey. Now consider this from the other direction. Voyager 1 has been flying for nearly 50 years. In those 50 years, it has covered approximately 14.5 billion miles. 1 light-year is 5.88 trillion miles. 50 years of continuous travel has gotten it to roughly 1/400th of a single light-year. Not 1 light-year, not 1/10th of a light-year, not 100th, 1/400th. To complete the journey at that rate would require another 17,550 years of continuous travel. On top of the nearly 50 it has already flown, and even then it would only be at the 1 light-year mark, not at any star, just at the distance of 1 light-year. The nearest star is more than 4 times further than that. This is not a criticism of Voyager 1. Voyager 1 is one of the greatest achievements in the history of exploration. It has returned data that changed how we understand the outer solar system. It has outlasted its original mission by decades. The people who built it and the people who have spent careers maintaining communication with it deserve enormous credit. The probe is a marvel. But as an interstellar vehicle, as a machine for crossing the distances between stars, it is essentially standing still. On the scale of the distances between stellar systems, 38,000 miles per hour is so slow, it might as well be zero. So what if we used more energy? What if we used nuclear power? In the late 1950s, a serious scientific program called Project Orion proposed exactly that. Not a nuclear reactor. Actual nuclear bombs. The spacecraft would carry hundreds or thousands of nuclear devices. It would detonate them one after another, dozens per minute, behind a massive armored plate at the back of the ship. Each detonation would produce a shock wave that pushed the plate. The plate would push the ship. Repeated pulses of nuclear explosions would accelerate the spacecraft to speeds no chemical rocket could approach. The physics works. Engineers spent years calculating the numbers carefully and in detail. A spacecraft of this design, given enough bombs and enough time to accelerate, could reach 3 to 5% the speed of light. Not 1%. 3 to 5% of the speed of light. At 5% the speed of light, crossing 1 light-year takes approximately 20 years. 20 years. Not 17,600 like Voyager. Not 1,560 like the Parker Solar Probe. 20 years. 20 years is within a human lifetime. A person who boards the spacecraft at 30 years old arrives at the destination at 50. Still alive. Still capable of doing work. Still able to see what they spent 2 decades traveling toward. For the first time in this conversation, we are looking at a number that connects to a human life. A number that a person could actually live through as a journey, rather than as an abstraction spanning civilizations. But Project Orion was never built. The Partial Test Ban Treaty of 1963 prohibited nuclear detonations in the atmosphere and in outer space. The political environment of the Cold War made the concept legally impossible to pursue. Beyond the politics, the engineering challenges were enormous. Thousands of precisely engineered nuclear devices, each detonating at exactly the right moment in exactly the right position. Any failure in that chain could be catastrophic. The radiation environment for the crew would be severe. The cost of manufacturing that many individual warheads to exact specifications was astronomical. The problem of launching such a system safely from Earth was never solved. Project Orion sits in history as one of the great roads not taken. A real idea, real physics, real engineering calculations, real enough to calculate in detail, never built in reality. What about nuclear power without explosions? A nuclear reactor generating electricity to power an ion drive. An ion drive works by electrically accelerating charged particles, ions, and ejecting them at high velocity out the back of the spacecraft. The thrust is tiny, genuinely tiny. Millinewtons, a fraction of the force needed to lift a small coin off a table. You would not feel it standing on the ship. It would not push you back in your seat. But it never stops. Day after day, week after week, month after month, year after year. The ion drive keeps pushing, and the accumulation of tiny constant pushes adds up into something real over years of operation. Velocity builds slowly, but it never stops building. NASA's Dawn spacecraft used this principle to accumulate more total velocity change than any spacecraft in history, all through the patient accumulation of tiny continuous pushes over years of operation. But even with a large nuclear reactor providing enormous power, nuclear electric propulsion would probably top out at about 1 to 2% the speed of light. At 1% the speed of light, crossing 1 light year takes exactly 100 years. 100 years. A full century. No one who boards the ship will be alive when it arrives. This is no longer a journey that any individual person experiences. It is a journey that a lineage experiences. This is the generation ship concept. A vessel large enough to sustain a human population across multiple generations of travel. The people who leave Earth will never see the destination. Their children might not either. Their grandchildren, born in space, raised in space, knowing nothing of Earth except stories, might be the ones to finally arrive. If the mission holds together that long, if the ecosystem survives, if the population stays healthy, if the mission's purpose survives being passed down through generations who never chose it, those are enormous if statements. The engineering challenges of keeping hundreds of people alive for a century in a closed system are staggering. The International Space Station is continuously resupplied from Earth. It is not a closed system. Everything it needs comes from outside. We have never built a life support system that can sustain human life in complete isolation for even a decade, let alone a century. We do not know how to do this. And the human challenges go beyond engineering. The people who depart choose to go. Their children do not choose. Their grandchildren do not choose. By the time the 4th generation is born, Earth is a myth their great-grandparents told. The mission that someone else signed up for generations ago belongs less and less to the people who must carry it out. What keeps a society together across generations inside a metal cylinder in empty space? Human societies on Earth, with all their freedom and options, struggle to maintain coherent purpose across centuries. Religions split, empires fall. What holds together when there is nowhere else to go? These questions do not have easy answers. They may not have answers at all. Now let us go deeper into why faster is not just an engineering problem, because this is where the physics becomes both fascinating and deeply discouraging. Einstein's theory of special relativity, published in 1905, tells us something fundamental and counterintuitive about motion and energy. As an object with mass accelerates, the energy required to continue accelerating it increases faster and faster as the speed approaches the speed of light, much faster. The relationship is not linear, it is not even simply exponential. As the speed approaches the speed of light exactly, the energy required approaches infinity, not a very large number, infinity itself. The energy required to accelerate a massive object to the speed of light is infinite. This means that no finite amount of energy can do it. Not a large amount, not an astronomically large amount, not even an unimaginably large amount. No amount. None. Zero finite energy equals 0 times infinity, which still cannot reach it. The speed of light is not a barrier that harder engineering can eventually overcome. It is a limit written into the structure of space-time itself. It is not like a wall that might be knocked down with enough force. It is more like trying to reach the edge of the universe by walking. There is no edge. The limit is not a thing you can run into and push past. It is built into the nature of space and time. And even well below that absolute limit, the energy requirements become staggering at speeds that matter for interstellar travel. To accelerate 1 kilogram of mass to 10% the speed of light requires energy equivalent to roughly 10,000 kilograms of rocket fuel, assuming perfect efficiency. 10,000 to 1. To reach 50% the speed of light with that same kilogram requires energy equivalent to about 300,000 kilograms. 300,000 to 1. To reach 90% the speed of light requires energy equivalent to nearly 3 million kilograms of fuel. 3 million to 1. These ratios are not linear. Going from 10% to 50% multiplies the velocity by 5, but multiplies the energy by 30. Going from 50 to 90% multiplies the velocity by less than 2, but multiplies the energy required by 10 more. The curve gets steeper and steeper. The closer you get to the speed of light, the more the energy requirement explodes. And all of these calculations assume 100% efficiency. Every single joule of energy converted perfectly and completely into forward motion with absolutely nothing wasted. No engine has ever achieved that. Chemical rockets convert only a few % of their fuel's energy into useful thrust. Even the most efficient ion drives waste significant fractions of their input. But even assuming perfect 100% efficiency, numbers of millions to 1 are staggering. Then there is the rocket equation. A spacecraft carries its fuel aboard. That fuel has mass. That mass must be accelerated along with everything else. To accelerate the fuel, you need to burn more fuel. To carry that extra fuel, you need even more fuel on top. The relationship spirals into territory where the fuel is almost everything. A spacecraft designed to reach 10% the speed of light using onboard fuel would need to be mostly fuel by mass. A spacecraft designed to reach 50% would need to be almost entirely fuel. The actual payload, the crew and their supplies and the mission instruments would be a tiny fraction of the total launch mass. This is the rocket equation. It is brutal, and it is why ideas that leave the fuel source behind are so appealing. Laser sails avoid the rocket equation entirely. The energy source stays on Earth. A powerful laser shines onto a large reflective sail. The pressure of the laser light pushes the sail and accelerates the spacecraft. The spacecraft carries nothing but itself. The rocket equation stops applying. The Breakthrough Starshot project proposes using ground-based lasers to push gram-scale spacecraft to about 20% the speed of light. 20%. At that speed, crossing 1 light-year takes 5 years. Reaching the Alpha Centauri system takes about 22 years. But these spacecraft cannot stop. There is no laser at the destination pushing from the other side. They arrive at 20% the speed of light and keep going. They fly through the Alpha Centauri system in a few hours and then disappear into the void forever. A flyby, not a stop, not a landing. A brief pass at 60 million miles per hour and then gone. This is the most realistic vision we currently have for near-term interstellar travel. A chip the size of a postage stamp, moving at 20% the speed of light, unable to stop, carrying almost nothing, never to return. And even this faces engineering challenges that have not been solved. Let us now think about scale in different ways, because numbers alone are not enough. We need to try to feel this. If you drive a car at 60 miles per hour without stopping, how long to drive 1 light year? 1 light year is 5.88 trillion miles. At 60 miles per hour, that is 98 billion hours. That is about 11.2 million years of driving. 11 million years. 11 million years ago, there were no humans. There were not even the earliest members of our genus Homo. The first stone tools appeared about 3.3 million years ago. The first members of our genus appeared about 2.5 million years ago. 11 million years ago, our evolutionary line had not yet separated from the other great apes. You would have had to start driving before anything recognizably human existed. You would drive for millions of years. Through the emergence of our earliest ancestors, through the first stone tools, through the first fire, through the first cave paintings, through the entire development of our species, through all of agriculture and writing and civilization and science and technology, and you still would not be there. What if you walked 3 miles per hour? 1 light year at 3 miles per hour takes approximately 224 million years. The first dinosaurs appeared about 230 million years ago. You would need to start walking just before the first dinosaurs evolved. You would walk through the Triassic. You would watch the dinosaurs rise. You would walk through the Jurassic. You would walk through the Cretaceous. You would watch the asteroid hit and the dinosaurs die 66 million years ago, and you would still have 66 million more years of walking ahead of you. You would walk through the age of mammals, through the emergence of primates, through the emergence of our species, through all of recorded history, and you still would not have covered 1 light year. What if you took a commercial flight, 575 miles per hour? 1 light year at that speed takes about 1.17 million years. Our species has existed for at most 300,000 years. You would need to have boarded the flight before Homo sapiens existed. Our entire species history, from our first appearance to this moment, would not be enough for the flight to complete. And even the fastest thing we have ever built, the Parker Solar Probe, needs 1,560 years. Now let us zoom out and place all of this in the context of the universe itself. The Milky Way galaxy contains somewhere between 100 billion and 400 billion stars. These stars are spread across a disk roughly 100,000 light-years in diameter. In our neighborhood of the galaxy, the average distance between neighboring stars is about 4 to 5 light-years. That is the average. One star to the next, nearest one. 4 to 5 light-years. The distance we have been calling essentially uncrossable is the average gap between neighbors in our corner of the galaxy. At Parker Solar Probe speed, crossing our galaxy from one side to the other would take about 156 million years. The nearest large galaxy, Andromeda, is about 2.5 million light-years away. Getting there at Parker Solar Probe speed would take about 3.9 billion years. The universe itself is about 13.8 billion years old. Reaching Andromeda would take longer than the Earth has existed. The observable universe extends about 46 billion light-years in every direction. These numbers no longer have meaning. They can only be stated and then sat with in silence. Let us try one more way to feel the scale. Build a scale model in your mind. Let 1 millimeter represent 1 light-year. 1 millimeter. At that scale, how large is our solar system? The solar system extends to about 100 astronomical units, which is about 0.0016 light-years. At 1 millimeter per light-year, the entire solar system would be smaller than the width of a human hair, invisible to the naked eye. On that map, the nearest star would be 4.24 millimeters away, less than half a centimeter. The Milky Way would be about 100 meters across. The nearest large galaxy would be 2.5 kilometers away, and the observable universe would stretch about 93,000 kilometers in every direction. That is nearly a quarter of the way to the moon. 1 millimeter. The solar system. Invisible. And we cannot travel 1 millimeter on this map. Now let us talk about something that changes part of this picture in a genuinely strange and confirmed way. Time dilation. Einstein's theory tells us that time is not a constant. Time does not flow at the same rate for everything everywhere. It stretches, it compresses. A clock that moves fast ticks more slowly than a clock standing still. Not as an illusion, not as a measurement artifact, as physical reality. Moving clocks really do tick more slowly. This is not theoretical. GPS satellites orbit Earth at high speed. Their onboard clocks tick measurably more slowly than clocks on the ground. The GPS system must correct for this in its calculations, or the positions it computes would drift by miles per day. Every time your phone calculates your location, it is accounting for the fact that time passes more slowly for fast-moving satellites than it does for you on the ground. Einstein's time dilation is engineered into your everyday technology. At 50% the speed of light, a moving clock ticks at 87% the rate of a stationary one. A 10-year trip from Earth's perspective feels like 8.7 years to the traveler. Real, but not dramatic. At 90% the speed of light, the moving clock ticks at 44% the rest rate. 10 years outside feels like 4.4 years inside. Less than half. At 99%, the moving clock ticks at 14% the rest rate. 10 years outside feels like 17 months inside. You leave. 10 years pass on Earth. You age barely more than a year. At 99.9%, the moving clock ticks at 4.5% the rest rate. 10 years outside feels like 5.5 months inside. What this means in practice, a person who could somehow reach 99%, the speed of light, could personally travel to Proxima Centauri in about 7 months of experienced time. Earth would age 4.24 years. The traveler would age 7 months. 7 months to the nearest star. This is the twin paradox. Two identical twins. One stays on Earth. One travels at near light speed to a distant star and back. When they reunite, the traveling twin is younger. Not as a trick of perception, not as a matter of measurement. Genuinely younger. Their cells have divided fewer times. Their telomeres are longer. Their body has aged less. Time really passed more slowly for them because of how fast they moved. Time dilation means that in principle, a human being who could reach very high fractions of the speed of light could personally experience a journey of hundreds of light years within their own lifetime. The distances compress for the traveler. The 100,000 light years across our galaxy could be experienced as years, not millennia, at 99.9% the speed of light. But the cost is everything left behind. A journey to a star 100 light years away and back at 99% the speed of light would take 200 years from Earth's perspective. You would leave at 30, travel for what feels like a few years to you, and return to find that 2 centuries had passed. Everyone you knew is dead. Their children are dead. Their grandchildren are old. The world has transformed in ways you never witnessed. You are a stranger in a future that built itself without you. The faster you go, the greater the gulf. Time dilation does not make interstellar travel free. It makes it personally survivable at the cost of all connection to the world you left. You can go. You cannot come back to the same moment, and we still need the energy to reach those speeds. Time dilation is a benefit waiting behind an energy barrier we cannot currently climb. Now let us think about what very fast travel would actually look like and feel like. Not the numbers, the experience. Imagine you are on a spacecraft moving at 50% the speed of light, months out from Earth. The solar system is behind you. You look at the stars, the sky is wrong. The stars ahead of you are bluer. Their light has been compressed by your approach, shifted towards shorter, more energetic wavelengths. The stars behind you are redder. Their light is stretched by your recession. This is the Doppler effect applied to light, not a subtle tint. A genuine color transformation affecting every star in your view simultaneously. More light appears to come from directly ahead than from any other direction. Relativistic beaming. The universe's light concentrates into a cone in front of you. At 50% light speed, the effect is visible and real. At 90%, the entire visible universe has compressed into a bright patch ahead, while the rest of the sky fades. The constellations are gone. Orion is unrecognizable. The Big Dipper has dissolved. Every pattern any human being ever named has been erased. You are no longer seeing the stars from Earth's vantage point. Nearby stars have shifted position against the background of distant ones, destroying every configuration that has ever appeared in a star chart. The silence is absolute, not the absence of noise, the structural impossibility of sound. You are in vacuum. Nothing can transmit it. The silence is not calm. It is permanent. It is the nature of the place itself. Your nearest neighbor is behind you, light minutes away and getting further each second. If something fails, help cannot come. If you send a message home today, it will take hours to arrive, and the reply will take hours to return. You are more isolated than any human being in history, more distant from any other person or life or signal than any of your ancestors ever were. And you are also the most extraordinary person who has ever existed in one specific way. Every breath you draw is the most distant breath any member of your species has ever drawn. Every moment you exist in that place is a first. The sky you see has never been seen by human eyes. The position you occupy in space is a position no human body has ever occupied before. That is not nothing. That is something worth noticing. Some people would go. Throughout all of human history, some people have always gone into unknown oceans in wooden boats, into unmapped territory on foot, into space, sitting on top of enormous amounts of explosive fuel aimed at a place no one had been. That impulse is part of what we are. When the technology exists, there will be people willing to use it. The problem is, the technology does not exist, and may not for a very long time, so where does that leave us? It leaves us here, on this planet, with telescopes and radio dishes and mathematical equations and an insatiable curiosity that refuses to be stopped by the mere impossibility of physically going somewhere. The James Webb Space Telescope can analyze the atmospheric chemistry of planets orbiting other stars. It watches starlight pass through a planet's atmosphere during transit and reads which wavelengths are absorbed. Different molecules absorb different wavelengths. From this, astronomers can determine what gases are present in an alien atmosphere from trillions of miles away, including biosignatures. Oxygen and methane together in an atmosphere would be a powerful signal for life. On Earth, both gases are produced by living organisms, and they react with each other continuously. They can only coexist if something keeps replenishing them. On Earth, that something is biology. Finding them together on another world would be extremely difficult to explain without invoking life. We have not found that signal yet, but we are looking for it right now, with instruments specifically built to detect it from this planet, without going anywhere. And if we find it, if we confirm that another world around another star carries the chemical marks of biology, The fact that we cannot go there does not diminish the discovery. It does not make the knowledge smaller. Knowing that we are not alone, knowing that life exists beyond Earth, knowing that the process which produced us is not unique to this one small planet in this one ordinary solar system. That knowledge would change everything. Distance cannot take that away. We have detected gravitational waves produced when black holes merged 1 billion light-years away. Ripples in space-time so tiny they compressed our detectors by less than the diameter of a single proton. We measured those ripples from here. We have mapped the large-scale structure of the universe across billions of light-years without leaving this solar system. We have observed the cosmic microwave background, light from 380,000 years after the Big Bang. Light that has been traveling for nearly 14 billion years, and we have read its structure in detail. All of this from one planet, without going anywhere, without crossing a single light year. The universe is not only reachable by ship, it is reachable by light and by mathematics, and by the particular kind of mind that looks up at the night sky and refuses to stop asking what is out there. 1 light year. Nearly 5,900,000,000,000 miles. At our fastest, more than 15 centuries to cross. By walking, 224 million years. By driving, 11 million years. By commercial flight, over 1 million years. And by looking, by measuring, by thinking, by building instruments sensitive enough to read the universe's own light. We are already there. That is what we are. A species that cannot go but cannot stop looking. A species that builds machines to see further and further and further. A species that decodes the chemistry of distant planets from its own backyard. A species that measures the merging of black holes 1 billion light-years away using vibrations smaller than an atom. We are not fast enough. We are not powerful enough. We are separated from the stars by distances that our greatest technology barely begins to address. And we are looking at them anyway. We are studying them anyway. We are finding out what they are made of, whether they have planets, whether those planets might have life, whether the universe we live in is inhabited beyond this one small world. We are reaching, even when we cannot arrive. We are exploring, even when we cannot go. That is not a limitation. That is who we are. 1 light year. We cannot cross it, and we already have. Tonight, we are going to talk about distance, real distance, the kind of distance that makes everything we have ever built look completely useless. We are going to ask one question. How long would it take us to travel 1 light year? And when you understand the answer, really understand it not just as a number but as a reality, you will never look at the night sky the same way again. 1 light year. It sounds simple. It sounds like something you could look up and understand in 30 seconds. But the more you think about it, the more it opens up into something that the human mind genuinely cannot hold all at once. It is not just a big number. It is a number so large that it breaks the way we normally think about space and distance and time. Before we get into it, if this kind of content makes you stop and really think, take a second to subscribe. It helps this channel grow and keeps more videos like this one coming. Now let us start from the very beginning. A light year is not a unit of time. This is the first thing most people get wrong. When they hear the word year, they assume it is measuring time. It is not. A light year is a unit of distance. It is specifically the distance that light travels in 1 complete year. And to understand what that means, you first have to understand how fast light actually moves. Light travels at 186,000 miles per second, every second, without slowing, without stopping, without any effort at all. 186,000 miles. every single second. To put that in context, the circumference of Earth, the distance all the way around our entire planet at the equator, is about 24,900 miles. In 1 second, light travels that full distance more than 7 times. In 1 second, not 1 minute, 1 second. While you blink your eyes, light has gone around the world 7 times. While you draw a single breath, light has circled the planet more than 20 times. Think about what that means. Most people will spend their entire lives and never travel more than a few 100,000 miles total. A person who flies frequently, who travels for work, who takes vacations across oceans, might accumulate 500,000 miles over a full lifetime. Light covers that distance in less than 3 seconds. 3 seconds. The time it takes to count to 3 out loud. Light is not just fast the way a jet is fast or a rocket is fast. Light moves at a speed that makes every other speed we experience feel like standing completely still. A commercial airplane moves at 575 miles per hour. Light moves at 670 million miles per hour. Light is more than 1 million times faster than a commercial airplane. A rocket leaving Earth moves at about 25,000 miles per hour. Light is more than 26,000 times faster than that rocket. These are not differences in degree, they are differences in kind. And yet, even at that extraordinary speed, covering 1 full year of distance adds up to something almost incomprehensible. A year has 365 days. Each day has 24 hours. Each hour has 60 minutes. Each minute has 60 seconds. Multiply all of that together and you get 31,536,000 seconds in a single year. Light moving at 186,000 miles per second for 31,536,000 seconds covers a total distance of approximately 5.88 trillion miles. That is 1 light year. 5.88 trillion miles. Written out as a number, it has 12 digits. 5,880 billion miles. In 1 year of constant travel at the fastest speed anything in the universe can move. Now hold that number. Hold it in mind while we ask the central question of this entire video. How long would it take us to travel that distance? Not light, us, with our spacecraft, with our rockets, with everything our civilization has actually managed to build. Let us begin with the fastest thing humanity has ever created. Not the fastest thing we have imagined, not the fastest thing in a film or a book, the actual fastest object that human beings have ever put into motion. The Parker Solar Probe. The Parker Solar Probe was launched by NASA in August of 2018. Its mission was to study the Sun from closer than any spacecraft had ever gone. Not just close to the Sun, inside the Sun's outer atmosphere, into a region called the corona, where temperatures reach millions of degrees and the solar wind originates. To complete this mission, the probe had to orbit the Sun repeatedly at extremely close distances. And each time it comes close, the Sun's gravity accelerates it faster and faster. At its closest approach to the Sun, the Parker Solar Probe reaches its maximum speed, approximately 430,000 miles per hour. That is 430,000 miles per hour. Let that land for a second. 430,000 miles per hour. That is the fastest any human-made object has ever moved. The all-time speed record for our entire civilization. Every spacecraft, every rocket, every satellite, every probe, everything we have ever launched, the fastest any of it has ever gone, was about 430,000 miles per hour. How fast is that really? A rifle bullet travels at about 2,000 miles per hour. The Parker Solar Probe moves 215 times faster than a rifle bullet. The fastest jet aircraft ever built The SR-71 Blackbird flew at about 2,200 miles per hour. The Parker Solar Probe moves nearly 200 times faster than that. A high-speed train travels at about 200 miles per hour. The probe moves 2,150 times faster than that train. By every standard of speed we experience in daily life, 430,000 miles per hour is almost impossible to comprehend, and it is still more than 1,500 times slower than light. Let that sink in. Our absolute fastest. Our greatest achievement in speed. The record holder. The fastest thing our civilization has ever built, and it is more than 1,500 times too slow to match the speed of light. Not twice too slow, not 10 times too slow, more than 1,500 times too slow. The gap between the Parker Solar Probe and the speed of light is not a gap that better engineering will close in a generation or two. It reveals the true scale of what we are dealing with when we talk about light years. So how long would it take the Parker Solar Probe to travel 1 light year? 1 light year is 5.88 trillion miles. At 430,000 miles per hour, the calculation gives you approximately 1,560 years. 1,560 years, not decades, not a century or two, 1,560 years. Let us be specific about what 1,560 years means. The Western Roman Empire collapsed in 476 AD count, forward 1,560 years from that moment. You arrive at roughly the year 2036. We are living just about at that mark right now, which means that if the Parker Solar Probe had been launched the day the Roman Empire fell, it would be arriving at the 1 light-year mark roughly today. The entire span from the fall of Rome to the present, all of the Middle Ages, the Renaissance, the Age of Exploration, the Scientific Revolution, the Industrial Revolution, the invention of electricity, the invention of the airplane, World War I, World War II, the space age, the internet, all of it, and the probe would just now be crossing the 1 light-year mark. And Proxima Centauri, the nearest star to our Sun, is not 1 light-year away. It is 4.24 light-years away. At Parker Solar Probe speed, reaching the nearest star would take more than 6,600 years. The first permanent cities appeared on Earth roughly 6,000 years ago. The first writing systems were developed about 5,000 years ago. The pyramids at Giza were built about 4,500 years ago. Humanity has not had writing as long as it would take our fastest spacecraft to reach the nearest star. The nearest star, not the center of the galaxy, not some distant corner of the Milky Way. The single nearest star to our Sun, 6,600 years. At our fastest speed. Now maybe you are thinking that the Parker Solar Probe was not built to travel to other stars. It was built to study the Sun. A spacecraft designed for a different mission might do better. So let us look at the spacecraft actually designed for the longest possible journeys. Voyager 1 was launched in 1977. It is currently the most distant human-made object that has ever existed. More than 14 billion miles from Earth, beyond the orbit of Neptune, beyond Pluto, beyond the outer boundary of the heliosphere, the bubble of solar wind that surrounds our solar system. Voyager 1 is traveling through interstellar space, the space between star systems, and it has been traveling for nearly 50 years without stopping. Voyager 1 was designed for distance. It was designed to travel as far as possible to study the outer planets and then keep going. It is our most experienced deep space traveler. And it is still operating. After nearly 50 years, still sending data home, faint signals that take more than 20 hours to reach Earth, even traveling at the speed of light. Voyager 1 moves at about 38,000 miles per hour. That is slower than the Parker Solar Probe, but still extraordinary. At 38,000 miles per hour, you could travel from New York to London in about 5 minutes. You could circle the entire planet in under an hour. You could reach the moon in roughly 6 hours. By any standard we use in daily life, 38,000 miles per hour is astonishing. So how long would it take Voyager 1 to travel 1 light year? At 38,000 miles per hour, the journey would take approximately 17,600 years. 17,600 years. Agriculture was invented about 10,000 years ago. Writing was invented about 5,000 years ago. Human civilization as we know it, cities and governments and written laws and organized religion and all the rest of it, has existed for maybe 6,000 to 7,000 years. Voyager 1 would need to travel for more than twice the entire history of human civilization to cover a single light year. Think about that from another direction. Voyager 1 has been flying for nearly 50 years. It has covered about 14.5 billion miles. 1 light year is 5.88 trillion miles. In 50 years of continuous travel, Voyager 1 has covered roughly 1/400th of a light year. Not 1 light year. 1/400th of 1 light year. To cover the full distance at the same rate would require an additional 17,550 years of continuous travel. 17,550 more years. The probe has been flying for 50 and covered 1/400th. At that rate, completing 1 light year would require starting over again 350 more times, each time running for 50 years. 350 more missions, each lasting 50 years, one after another, to cover 1 light year. This is not a criticism of Voyager 1. Voyager 1 is one of the greatest achievements in the history of human exploration. It has returned irreplaceable scientific data. It has traveled farther than any human-made object ever. It represents engineering genius and scientific vision that extended decades beyond its original mission. The people who built it and the people who have spent decades maintaining contact with it deserve immense credit. But as an interstellar vehicle, it is essentially stationary. On the scale of the distances between stars, Voyager 1 might as well not be moving at all. So let us think bigger. What if we used the power of the atom? In the late 1950s, a group of physicists and engineers working under a program called Project Orion developed a serious proposal for a new kind of spacecraft. Not a spacecraft powered by chemical fuel. A spacecraft powered by nuclear explosions. The idea was direct and dramatic. Detonate nuclear bombs behind the spacecraft, one after another, at a rapid rate. Each explosion would push against an enormous armored plate at the back of the ship. The repeated pushes would accelerate the spacecraft to extraordinary speeds. This is not science fiction. The physics works. Engineers calculated the numbers carefully. A spacecraft of this type, given enough bombs and enough time to accelerate, could theoretically reach speeds of 3 to 5% the speed of light. 3 to 5%. Not a fraction of a percent the way Voyager 1 manages. Not even 1%. 3 to 5% of the speed of light. A meaningful, significant fraction. At 5% the speed of light, crossing 1 light year takes approximately 20 years. 20 years. Let that land. Not 17,600 years like Voyager. Not 1,560 years like the Parker Solar Probe. 20 years. A journey within a human lifetime. A person who boards the spacecraft at age 30 would arrive at the destination at age 50. Still alive, still active, still able to do work, still able to see what they traveled 20 years to reach. For the first time in this conversation, we are looking at a number that a human being could actually experience as a journey rather than as an abstraction that spans civilizations. But Project Orion was never built. The Partial Test Ban Treaty of 1963 prohibited nuclear detonations in the atmosphere and in space. The political environment of the early nuclear age made the concept impossible to pursue legally. And the engineering challenges were enormous. You would need thousands of precisely engineered nuclear devices, each one detonated at exactly the right moment and exactly the right position. Any failure in that sequence could be catastrophic. The radiation levels for the crew would be severe. The cost of manufacturing that many nuclear warheads would be astronomical. Project Orion is one of the great roads not taken in the history of space exploration. A real idea backed by real physics. Real enough to calculate, never real enough to build. What about nuclear propulsion that does not require explosions? What about using a nuclear reactor to power a propulsion system more continuously and more quietly? There is a concept called nuclear electric propulsion. A nuclear reactor generates electricity. That electricity powers an ion drive. An ion drive works by electrically accelerating charged particles, ions, to high velocity and ejecting them out the back of the spacecraft. The thrust produced by an ion drive is tiny, smaller than tiny. We are talking about millinewtons of force, less than the force needed to lift a small coin off a table. You would not feel it if you were standing on the ship. It would not push you back in your seat. It is a whisper of force, but it never stops. An ion drive does not burn for a few minutes and go dark like a chemical rocket. It pushes continuously, day after day, week after week, month after month, year after year. And that constant gentle push accumulates into something significant. Velocity builds slowly, but it never stops building. Over years of operation, the accumulated velocity of an ion drive approaches speeds that a brief explosive burn could never reach. NASA used this principle on the Dawn spacecraft, which traveled to study the asteroid Vesta and the dwarf planet Ceres. Dawn used solar-powered ion drives, not nuclear ones, but the physics is the same. Over the course of its entire mission, Dawn changed its velocity by a total of about 25,000 miles per hour. That is more total velocity change than any other spacecraft in history, all of it achieved through the patient accumulation of small, continuous pushes over years of operation. But even 25,000 miles per hour of accumulated velocity change over several years is not nearly fast enough for interstellar travel. With a large nuclear reactor providing far more power than Dawn's solar panels could supply, nuclear electric propulsion might realistically reach 1 to 2% the speed of light. Not 5% like Project Orion, 1 to 2%. At 1% the speed of light, crossing 1 light year takes exactly 100 years. 100 years, a full century. The people who board the ship will not be alive when it arrives. This is no longer a journey any individual experiences. It is a journey that a lineage experiences. The children of the crew, or their grandchildren, would be the ones to finally see the destination. This is the concept of the generation ship, a vessel large enough and self-sufficient enough to sustain a human population across multiple generations, across decades or centuries of travel through empty space between stars. The concept of a generation ship raises questions that go far beyond engineering. How do you feed hundreds of people indefinitely in a system where nothing can be resupplied? Every calorie must be grown aboard. Every molecule of oxygen must be produced aboard. Every drop of water must be recycled and recycled again. Every waste product must be reprocessed into useful materials. We have never built a life support system that that can sustain human life in complete isolation for even 10 years, let alone 100. The International Space Station is continuously resupplied from Earth. Multiple cargo ships per year deliver food and supplies. It is not a closed system. It depends entirely on external inputs to survive. Biosphere 2, an experiment in the early 1990s that attempted to create a self-sustaining enclosed ecosystem in Arizona, tried to sustain 8 people using only internal resources for 2 years. Within months, there were serious problems. Oxygen levels fell unexpectedly. Food production was not sufficient. The experiment revealed how little we actually understand about creating and maintaining closed ecological systems. And it was on Earth where outside help was available. On a generation ship traveling between stars, there is no outside help. Whatever fails must be fixed with what is aboard. Whatever runs out must be grown or recycled or done without. The human social challenges are just as profound as the engineering ones. The people who depart choose to go. Their children do not choose. Their grandchildren do not choose. By the time the 3rd generation is born aboard the ship, Earth is something their grandparents talked about. A story. Not a place any living person has seen. The mission that someone else decided before any of them were born becomes less and less their own. What holds a society together when its founding purpose belongs to people who are now many generations dead? These are not engineering problems that can be solved with better materials. They are human problems. And human societies on Earth, with all their freedom and all their options, rarely maintain coherent purpose across more than a few centuries. Religions split. Empires crumble. Institutions transform beyond recognition. There is not much reason to expect a metal cylinder traveling through darkness to do better. But suppose every one of those challenges was somehow solved. What would the actual travel time look like for stars in our neighborhood? At 1% the speed of light, Proxima Centauri at 4.24 light-years would take 424 years, more than 4 centuries. The United States has not existed for 4 centuries. At 1% the speed of light, a star 10 light-years away takes 1,000 years. A star 20 light-years away takes 2,000 years. A star 100 light-years away takes 10,000 years. These are the nearby stars, the ones within our immediate cosmic neighborhood, and they are all centuries to millennia away at 1% the speed of light. Now let us talk about why going faster is not simply a matter of building a better engine, because this is where the physics becomes deeply interesting and deeply discouraging at the same time. In 1905, Albert Einstein published the theory of special relativity. Among many other things, this theory tells us something counterintuitive and absolutely fundamental about the relationship between speed and energy. As an object with mass accelerates, the energy required to accelerate it further increases, not proportionally, not in a simple linear relationship. The energy requirement increases faster and faster as the speed approaches the speed of light, much faster. At low speeds, the extra energy required to go a bit faster is small and manageable. At 10% the speed of light, the correction is less than 1%. But as the speed climbs toward light speed, the correction becomes enormous. At 90% the speed of light, the energy required to go even slightly faster has grown by a factor of several times what you would calculate classically. At 99%, the factor is about 7. At 99.9%, it is about 22. And as the speed approaches light speed exactly, the factor approaches infinity. Infinity, not a very large number, infinity itself. The energy required to accelerate a massive object to exactly the speed of light is infinite. No finite amount of energy can do it. Not a large amount, not an astronomically large amount. No amount at all. The speed of light is not just a very high speed that we have not managed to reach yet. It is a fundamental limit built into the structure of space-time itself. It is not an engineering barrier. It is a law of nature. And even well below that absolute limit, the energy numbers become staggering quickly. Let us look at specific examples. To accelerate 1 kilogram of mass to 10%, the speed of light requires energy equivalent to roughly 10,000 kilograms of rocket fuel, assuming perfect efficiency. 10,000 kilograms of fuel to push 1 kilogram of payload to 10% light speed, a ratio of 10,000 to 1. To reach 50% the speed of light with that same 1 kilogram of payload requires energy equivalent to about 300,000 kilograms of fuel. 300,000 to 1. To reach 90% the speed of light requires energy equivalent to nearly 3 million kilograms of fuel. 3 million to 1. Notice how these ratios escalate. Going from 10% to 50% light speed multiplies your velocity by 5, but multiplies the required energy by 30. Going from 50% to 90% multiplies the velocity by less than 2, but multiplies the energy by 10. The relationship becomes increasingly brutal the faster you go. And these numbers assume 100% efficiency. Every joule of energy converted perfectly and completely into forward motion, with absolutely nothing wasted. No engine in history has achieved that. Chemical rockets convert only a few % of their fuel's chemical energy into useful thrust. Even the best ion drives waste significant fractions of their input power. But even with perfect 100% efficiency, the numbers are extraordinary. There is also the rocket equation to consider. When a spacecraft carries its fuel aboard, that fuel has mass. That mass must be accelerated along with everything else. But to accelerate the fuel, you need more fuel. And to accelerate that extra fuel, you need even more fuel on top of that. The relationship compounds rapidly into territory where the fuel vastly outweighs everything else. A spacecraft designed to reach 10% the speed of light using onboard fuel would need to be mostly fuel by mass. Most of what it carries would be fuel, not crew, not supplies, not equipment, not the mission itself. Just fuel to push other fuel. A spacecraft designed to reach 50% light speed using onboard fuel would need to be almost entirely fuel. The payload would be a tiny fraction. A spacecraft designed to reach 90% would face numbers so extreme that the concept becomes essentially impractical. This is why ideas that leave the fuel source behind are so appealing. If the fuel stays on Earth, you do not have to carry it. You do not have to accelerate it. The rocket equation stops applying. You sidestep one of the most brutal constraints of interstellar travel entirely. This is the core idea behind laser sails. A powerful laser on Earth or in orbit shines a beam onto a large reflective sail attached to a tiny spacecraft. The pressure of the laser light pushes the sail. The spacecraft accelerates. The fuel, the laser itself, stays behind. The spacecraft carries nothing but itself. The Breakthrough Starshot project, announced in 2016, takes this idea seriously. Funded by private investors and backed by scientists including the late Stephen Hawking, Breakthrough Starshot proposes to build ground-based lasers powerful enough to accelerate gram-scale spacecraft to about 20%, the speed of light. 20%, not 1%, not 5%, 20%. At 20% the speed of light, crossing 1 light year takes 5 years. 5 years. Traveling to the Alpha Centauri system at about 4.37 light years from Earth would take about 22 years. The data would then take another 4.37 years to travel home at the speed of light. Total time from launch to receiving the first data, roughly 26 years, within a human lifetime, within the career of a scientist who helps design the mission. But Breakthrough Starshot cannot send people. It cannot send a spacecraft that carries any significant payload. We are talking about a probe the size and weight of a postage stamp, a gram-scale chip with miniaturized cameras and sensors attached to a sail a few meters wide. And there is another fundamental problem. The sail cannot slow down. There is no laser at the destination to push against from the other direction. The spacecraft arrives at Alpha Centauri at 20% the speed of light and keeps going. It flies through the system. It has perhaps a few hours where it is close enough to image the planets and measure their properties. Then it continues out the other side into empty space forever. A flyby, not an orbit, not a landing, not a base, a single brief pass at extraordinary speed, and then gone forever. This is the most realistic version of interstellar travel we can currently envision, building in the foreseeable future. A chip on a laser beam, unable to stop, carrying almost nothing, never to return. And even this faces enormous engineering challenges that have not yet been solved. Let us now think about scale in a different way. Numbers alone are inadequate. Let us try to build intuitions. The distance from Earth to the Sun is about 93 million miles. This is called 1 astronomical unit, and it is the baseline we use to measure distances within our solar system. Light covers this distance in about 8 minutes. Neptune, the outermost planet, orbits at about 30 astronomical units from the Sun. Light takes about 4 hours to reach Neptune. Voyager 1, after nearly 50 years, is now at about 160 astronomical units from the Sun. 1 light-year is 63,241 astronomical units, 63,000 times the distance from Earth to the Sun. On the scale of our solar system, 1 light-year is enormous. Here is a way to visualize this. Imagine building a scale model where the distance from Earth to the Sun is represented by 1 foot. 1 foot. At that scale, how far away is the nearest star? 63,000 feet. That is about 12 miles. You would need to drive 12 miles away and place a tiny dot to represent Proxima Centauri, our nearest stellar neighbor. In that same scale model, the Milky Way galaxy would be about 1.7 billion miles across. The nearest galaxy, Andromeda, would be over 40 billion miles away. The observable universe would extend trillions of miles in every direction, all from a scale where the Earth-Sun distance is just 1 foot. Let us try another way to feel this distance. A car driving at 60 miles per hour without stopping, without traffic, without ever slowing. How long to drive 1 light-year? 1 light-year is 5.88 trillion miles. At 60 miles per hour, that is approximately 98 billion hours. There are 8,760 hours in a year. That is approximately 11.2 million years of continuous driving. 11 million years. 11 million years ago, there were no humans. There were not even the earliest members of our genus. The first stone tools appeared about 3.3 million years ago. The first members of the genus Homo appeared about 2.5 million years ago. 11 million years ago, our evolutionary line had not yet separated from the other great apes. You would have had to start driving before anything recognizable as human existed on Earth. You would still be driving today, and you would not have arrived. What about walking? 3 miles per hour at a comfortable walking pace. 1 light-year at 3 miles per hour takes approximately 224 million years. The dinosaurs appeared about 230 million years ago. You would need to have started walking just before the first dinosaurs evolved. You would walk through the entire 165 million years of the age of the dinosaurs. You would watch them go extinct at the 66 million year mark. You would walk for 66 million more years through the age of mammals, through the emergence of primates, through the emergence of our species, through all of recorded history, and you would still not have arrived. What if you flew on a commercial airplane? A modern airliner cruises at about 575 miles per hour. 1 light year at 575 miles per hour takes approximately 1.17 million years. Modern humans have existed for, at most, 300,000 years. You would need to have boarded the plane before our species existed. Our entire evolutionary history, from the first anatomically modern humans to the present day, would not be enough time to complete the flight. And even the Parker Solar Probe, moving at 430,000 miles per hour, needs 1,560 years. Now let us zoom out and place 1 light year in the context of the universe at large. The Milky Way galaxy contains somewhere between 100 billion and 400 billion stars. These stars are spread across a disk roughly 100,000 light-years in diameter. In our neighborhood of the galaxy, the average distance between neighboring stars is about 4 to 5 light-years. That means the distance we have been discussing, the distance that takes 1,560 years for our fastest probe, is just the average gap between one star and its nearest neighbor. Just one step. In a galaxy containing hundreds of billions of stars, the Milky Way is about 100,000 light-years across. At Parker Solar Probe speed, crossing the galaxy from one side to the other would take about 156 million years. The nearest large galaxy, Andromeda, is about 2.5 million light-years away. At Parker Solar Probe speed, reaching Andromeda would take about 3.9 billion years. The universe itself is about 13.8 billion years old. These numbers stop having meaning. They cannot be felt. They can only be stated and then sat within silence. But let us try to feel them a different way. There is a thought experiment that helps. Imagine a map of the universe where 1 light year is represented by 1 millimeter. 1 millimeter on this map. At that scale, how large would our solar system be? The solar system extends to about 100 astronomical units. At that scale, the entire solar system would be smaller than the width of a human hair. It would not be visible to the naked eye on this map. And how large would the map need to be to show the observable universe? About 93 billion light-years in diameter. At 1 millimeter per light-year, that is 93 billion millimeters. About 57 million miles. You would need a map nearly 60 million miles across to show the observable universe at the scale where 1 light-year equals 1 millimeter. A map that would stretch from Earth to the Sun and beyond. On that map, our solar system is a speck too small to see. Our galaxy is a smear about 62 feet across. The nearest galaxy is about half a mile away. The visible universe extends nearly 30 million miles in every direction. 1 light-year, 1 millimeter on this map, and we cannot cross it. Now let us talk about something that changes part of the picture. Something real and confirmed and genuinely strange. Time dilation. Einstein's theory of special relativity does not only set a speed limit, it also tells us something profound about the nature of time itself. Time is not a constant. It does not flow at the same rate everywhere. It is elastic. It stretches and compresses depending on how fast you are moving. Specifically, a clock that is moving fast ticks more slowly than a clock that is standing still. not as an illusion, not as a measurement error, as a genuine physical reality. This has been confirmed directly. Atomic clocks placed aboard high-speed aircraft have been compared to identical clocks left on the ground. The clocks on the aircraft ticked slightly more slowly, by exactly the amount that Einstein's equations predict. GPS satellites orbit Earth at high speed, and their onboard atomic clocks tick measurably more slowly than clocks on the ground. If the GPS system did not correct for this effect in its software, the positions it calculated would drift by several miles per day. Your phone corrects for Einstein's time dilation every time it calculates your location. Time dilation is not an abstraction. It is engineered into technology you use every day. At the speeds of everyday life, the effect is so small as to be undetectable without precision instruments. But as speeds approach the speed of light, the effect grows rapidly. At 50% the speed of light, a moving clock ticks at about 87% the rate of a stationary clock. A journey that takes 10 years from Earth's perspective feels like 8.7 years to the traveler. A real difference, but not dramatic. At 90% the speed of light, the moving clock ticks at about 44% the rate of a stationary clock. A 10-year journey from Earth's perspective feels like 4.4 years to the traveler. Less than half. You have aged less than half as much as the people you left behind. At 99% the speed of light, the moving clock ticks at about 14% the rest rate. A 10-year outside journey feels like about 17 months to the traveler. You leave, 10 years pass on Earth, and you have aged barely more than a year. At 99.9% of light speed, the moving clock ticks at about 4.5% the rest rate. A 10-year outside journey feels like about 5.5 months inside the ship. What this means is that a person who could somehow reach 99% the speed of light could personally travel to Proxima Centauri, 4.24 light-years away, in about 7 months of personal experience time. Earth would age 4.24 years during the trip. The traveler would age 7 months. They would arrive at the nearest star having grown older by less than a year. This is the twin paradox. Two twins. One stays on Earth. One travels at near light speed to a distant star and back. When they reunite, the traveling twin is younger, not as a matter of perception, not as a relative measurement. Genuinely, physically younger. Their body has aged less. Their cells have divided fewer times. They have experienced less time. Time itself passed more slowly for them because they were moving fast. Time dilation means that in principle, a human being could experience a journey of hundreds of light years within their own lifetime. The universe shrinks for very fast travelers. The 100,000 light years across our galaxy would be experienced as a much shorter journey by someone moving at 99.9% the speed of light. From their perspective, the galaxy could be crossed in years rather than millennia. But the cost of this compression is profound. Suppose you travel to a star 100 light years away at 99% the speed of light. From Earth's perspective, the journey takes just over 100 years. You experience about 14 years. You arrive still relatively young. But when you look back toward Earth, 100 years have passed. Everyone you knew is dead. Your children have grown old and died. Your grandchildren are elderly. Your great-grandchildren are middle-aged. The world has changed in ways you did not witness. You are a time traveler arriving in your own future. And the faster you go, the more extreme the gap becomes. At 99.9%, crossing 100 light years takes 100 years from Earth's perspective, but only about a year and a half from yours. You arrive having aged less than 2 years. Earth has aged a century. Time dilation does not make interstellar travel free. It allows the individual to survive the journey personally at the cost of everything they left behind. Every relationship, every connection, every context that gives a life meaning. You can go. You just cannot return to the same world you left. And we still need the energy to reach those speeds. The energy problem does not go away because time dilation exists. Time dilation is a feature available at the destination, inaccessible until you have already solved every other problem. Getting to 99% the speed of light in the first place requires extraordinary energy and engineering that we cannot currently provide. Time dilation is a benefit waiting behind a wall we cannot yet climb. Let us also think about what the practical experience of near light speed travel would be like. Not the math, the experience. You are aboard a spacecraft moving at 50% the speed of light. You are months out from Earth. The solar system is a distant memory. You look out a viewport at the stars. The sky is wrong. The stars ahead of you are bluer than they should be. Their light has been compressed by your approach, shifted to shorter, more energetic wavelengths. The stars behind you are redder, their light stretched by your recession. This is the Doppler effect applied to light itself, not a subtle tint, a genuine color shift affecting every star in your field of view. The distribution of light in the sky is also distorted. More brightness seems to come from directly ahead than from any other direction. This is relativistic beaming. The faster you move, the more the light of the universe concentrates into a cone in front of you. At 50% light speed, the effect is significant but manageable. At 90%, the entire visible universe has compressed into a bright patch ahead of you while the rest of the sky grows dark. The familiar constellations are gone. Orion is unrecognizable. The Big Dipper has scattered into a meaningless arrangement. Every pattern humanity has ever named in the night sky has dissolved because you are no longer seeing the stars from Earth's vantage point. The nearby stars have shifted their apparent positions against the background of distant ones, erasing every configuration that exists in any star atlas ever made. And the silence. A silence unlike anything on Earth. Not the absence of noise, the absence of the possibility of noise. You are in vacuum. There is nothing to transmit sound. There is no medium for it. The silence is not calm, it is absolute, permanent, structural. Your nearest neighbor is light minutes behind you and getting further by the second. If something breaks, help is not coming. If someone falls ill, there is no hospital within reach. If you send a message home today, it will take minutes or hours or eventually years to arrive. The reply will take just as long to return. You are more isolated than any human being in history. Farther from any other person, any other life, any other sound or signal than any of your ancestors ever were. And somehow, in the middle of that, you are also the most extraordinary person who has ever lived. Every breath you draw is the most distant breath any human being has ever drawn. Every moment is unprecedented. The sky outside your window has never been seen by human eyes before. Everything about where you are is singular and irreplaceable and unlike anything that has come before. Some people would make that trade. Throughout all of human history, some people have always made that trade. The history of exploration is the history of people who found the known world insufficient and walked into the unknown anyway. That impulse is not going away. It is part of what we are, but wanting to go and being able to go are very different things. And right now, we cannot go. Not to the stars, not even to the nearest one. Not in any way that connects to a human life lived on human timescales. So where does this leave us? What do we do with the knowledge that the universe is so vast and we are so slow? One answer is that we keep looking. We cannot go to the stars, but we can read their light. And that light carries information. Enormous amounts of information. The James Webb Space Telescope, launched in December 2021, can analyze the atmospheric chemistry of planets orbiting other stars. It does this by watching starlight pass through a planet's atmosphere as the planet transits in front of its star. Different gases absorb different wavelengths of light. By analyzing which wavelengths are missing from the transmitted light, astronomers can identify what molecules are present in the atmosphere of a planet trillions of miles away. This includes biosignatures, chemical signals that might indicate life. The combination of oxygen and methane in an atmosphere would be a powerful indicator. On Earth, both gases are produced by living organisms. They react with each other and destroy each other continuously. They can only coexist in an atmosphere if something is constantly replenishing them. On Earth, that something is life. If we found them together in an alien atmosphere, it would be extremely difficult to explain without invoking biology. We have not found that signal yet. But we are looking. We have instruments sensitive enough to read the chemistry of a planet's atmosphere from trillions of miles away. That is an extraordinary achievement by any measure. And if we find the signal, if we confirm that another world, orbiting another star, bears the chemical marks of life, the fact that we cannot physically go there does not diminish the discovery. Knowing that we are not alone, that life arose somewhere else, that the process which produced us is not unique to Earth, would be among the most transformative realizations in the history of our species. The distance would not matter. The knowledge would. Knowing that the universe is inhabited, that life is not a cosmic accident limited to one small planet, would change everything about how we understand our place in things.